All right, thanks. Thanks, Michelle. So my name is Liang from University of Washington, and you have seen the kind of level spring from the previous talk. So today I'm going to talk about Ondulé, which is about designing and controlling 3D printable springs. How can we enable designers to embed parameterizable springs in 3D printed objects? To address this question, we create Ondulé. Here's a sneak peek of the tool, where the designer can select the rigid arms of this little guy and convert it into a spring man using springs. Before we move to the details, let's take a step back and ask a bigger question, like how can we add deformation to 3D printed objects? So researchers has explored a lot of mechanical structures to make deformable and functional 3D printed objects, such as linkages, repetitive lattice patterns, embedded cells as metamaterial, telescoping structures, joints, and bendable wires. However, one of the most common deformable structures in manufacturing that has not been studied in research community is helical spring. So helical spring offers three major benefits which make it very attractive to explore. First, they support a variety of deformation behaviors such as compress, extend, twist, and bend. They can store and release potential energy, and they can be used decoratively to follow simple 3D geometries. But there are two key challenges in this area. The mechanical performance of 3D printed springs are not known yet, and design, customize, and control spring deformation behaviors is very hard for people to design. So to address these challenges, we create Ondulé by answering the following three questions. Because of the anisotropic characteristics of laser-wired 3D printing, we want to ask, do 3D printable springs follow mechanical theory? And taking the advantage of 3D printing, rather than using the off-the-shelf springs, we can actually customize the behaviors, but how can we isolate the intermixed behaviors in a spring? And further, how can we lower the barrier to create and control the springs in the CAD tools? To answer the first question, we did a set of mechanical experiments. So from the spring theory, we learned that the deformation behavior is affected by the material properties, Young's modulus, shear modulus, and a set of spring parameters like the spring diameter, wire thickness, and also the turn numbers. So we did three experiments. The first one, we are trying to derive the values of shear modulus and the Young's modulus. And then we did tensile and torsion experiments with 3D printed springs. So in my talk, I'm going to show one of the tensile tests. Please refer to my paper for more details about other experiments. For the test, we printed 17 3D printed springs by varying different parameters. And as you can see here on the left, we fix the spring in the load frame, and the grips pull the spring apart until it breaks. And actually, we can measure the stiffness K from the load frame. And the slope of this blue curve in the graph actually shows the stiffness K. And since we know all the parameters values, so we can actually calculate the stiffness K prime. And then we can compare the K and K prime in our tests. Here shows the results of the comparison by varying different turn numbers. As you can see here from the results of tensile and torsion tests, we can say the tensile and the torsion behaviors of 3D printed helical springs closely mirror the theoretical predictions. And this actually informs the development of our design tool, where the user can parameterize and control the spring by changing the parameters. All right, so in a default spring, all the behaviors are intermixed. So, how can we isolate the deformation behaviors? With 3D printing, we can actually use the space inside the spring. And yes, we create a set of deformation techniques. We use mechanical joints to support two types of behavior type here. Individual behaviors include linear only, which means only compress and extend, and twist only, bend only. And the compound behaviors include linear and twist, bend and twist, and of course a free-form spring without any joints. So let's take a closer look at each joint design. For compress and extend only, we use a prismatic joint design. The slider only moves along the predefined rail in the shaft. A groove latching mechanism can be added to the endpoint of the rail guide to lock the spring at the fully compressed or extended states. This is how the joint is embedded in the spring. And for the twist only, we use a reference joint. It has a circular disc inside a bearing socket, so we can rotate the rod. To support bending only in the plane, we create a chain of knuckle joints from nose to tail. And a single knuckle joint contains a cylindrical rod located inside a cylindrical socket, and the rod and socket share the same axis, so it can only bend in one plane. For the linear and plus compound behavior, we use a cylindrical joint, which replaces the slider with a disc, so the joint can move linear and also rotate. And we can do the linear compression, expansion, and twisting here. And finally, for the bend and twist, we apply a chain of ball joints so it can do unidirectional bending. You can rotate and bend in different directions. And to maintain the simple geometry in the original model, we also added the decorative spring when the deformation spring is added. Like the seahorse body here, the shape is maintained by the same decorative spring. All right, so we have verified the 3D printed spring performs like the spring theory suggested, and also explored different joints for isolating the behaviors in the spring. And then we built a design tool for novices to add deformation behavior to static 3D printed objects using embedded springs and joints. The design tool was built as a plugin for Rhino, and it consists of 3 parts: spring generation, spring stiffness control, and also spring behavior design with joints. Now let's take a look at how each part works. First, to convert a part of the model into a spring, the user selects a body and then click the Convert to Spring button, and the tool will generate the deformation and decorative springs. The user can change the spring length in the model directly, and the spring can be updated. So to generate the springs, we first compute the medial axis, which is the skeleton of the selected body. Then we use the sample points on the medial axis to calculate the body's size and check if there's enough space for the internal joint. If the body is not the regular cylinder, a decorative spring is also generated. And then, using the Rhino spiral command and the default spring parameters, we actually can create a spiral, the spring, around the medial axis. By sampling on the medial axis and generated the generated spiral curve, we can find another spiral around using the ray tracing technique. Then we use the new spiral to generate the decorative spring. Here's a quick demo of selecting the body and converting it to a spring. A default spring will be generated here, and then the user can change the length in the model. And the spring will be updated. After the spring is generated, we can control the spring stiffness by dragging the slider bars in this interface. We provide 2 ways to change stiffness. The user can input an abstract stiffness or precisely control spring parameters, such as Y thickness and the pitch between the core turns. The spring will be updated in the model, and this video actually shows how the user controls the stiffness through the interface. And then you can see the spring is actually changing and updated in the model. Lastly, when the user adds a joint design in the spring, the tool allows the user to specify values of deformation. For example, the user can specify the amount of compression and extension in a prismatic joint. The joint will be updated in the model as well. This explosive figure shows how each part of the joint is generated in my tool. And we create 5 interfaces for different joint designs. For example, for bend-only design, we allow the user to specify the bending direction and the angle. And here, the video shows the user specify the compression and the extension for a prismatic joint, and also specify the bending angle and the direction for a chain of knuckle joints. So to demonstrate the potential of our approach, we also built a set of applications. Of course, the first one is jack in the box. So we use two springs here to make the jack rotate when it pops up. And in the rocket launcher application, we convert the red smoke part into a spring, and then we add the latch at the bottom. When the user pulls the latch, the spring will release the energy and shoot the rocket. And we can store different energy in the spring by controlling the spring stiffness. For example, we can use a stiffer spring here to make the rocket fly higher. Unlike the off-the-shelf hand exerciser, we can customize each spring for different finger strength practice. By using external electronics, we can 3D print a tangible prop for story character authoring. Here we attach a Hall effect sensor and a piezo on the prop. And let's check how it works. So when you extend the neck, it will turn into a giraffe. And then when you push it up and down, it will talk. And then you press it back, it will go back to a horse. You pat the body, it will run. Finally, so we work with a mechanical engineering team for accessible device, cutting device. So in this device, we have these springs, right? So the user can customize the spring for their use requirements, because some people may have different muscle weakness levels. All right. So also we can achieve different spring behaviors by inserting joints. The size of the object is limited to minimum joints that we can print. We can use high-resolution printers to resolve this problem. And as I mentioned before, the anisotropy of 3D printing might affect the robustness of the 3D printed springs. In an object that has many springs, for example, it can not always be print out all the springs in a robust way or in their best printing settings. So a possible solution is to use another approach called print and assemble, or we can use a 5DOF 3D printer. And finally, although the current tool provides a preview of the generated springs, interactive physical simulation should be added in the future. So to show the effects of external forces or the weight of the spring, and see how the spring really performs in the real world. So to summarize, we introduced a new approach to allow novices to convert a static 3D shape into a deformable object with embedded 3D printed springs and joints. We did some mechanical experiments, and we created a set of techniques and built the design tool, and also we created a set of applications. And that's all. Thank you. I'm happy to take questions.
Hey, Liang, great work. I'm Sai from Carnegie Mellon University. So can you talk a little bit about using sort of different materials for making springs? For instance, I'm assuming different materials have different like load carrying capacities and things like that, right?
Yes. So at the very beginning of this project, we explore different materials like PLA, ABS, and right now we are using TPLA, which is called tough PLA. We think it's more robust than PLA. But as I said, in the first experiment, we try to derive the values of the material properties like shear modulus and Young's modulus. And to demonstrate this approach, we just examine the values for TPLA in this case. But in the tool, actually, we envision that the user can add, or the system can provide the material values for the user. And then, since we have the values, we can inject these values in the formula and create this prediction or the preview in the tool. Yeah, I agree with you, like different materials have different behaviors and different results. So, but I think the key part of this approach is like we create this end-to-end pipeline, and the user can change the parameters in the tool, and the tool can do whatever with the different materials.
Hi, I'm Faraz from MIT CSIL. Really
Can
cool
you hold
work.
the mic higher?
It's not.
Hold the mic higher to your face.
Sorry. I'm Faraz from MIT CSIL. Really cool work. Thanks for the talk. I wanted to ask about how do you constrain the model to actually print the spring? Because I imagine if you like even change the orientation of that unicorn, you might have to add support to it, to just make it print.
Yeah.
So how do you inform the user that this model might not print this orientation, so you might have to change it?
I think this question is about two parts. The first one is about how to print the objects in a certain way, right? So we explore two types of 3D printers. Using makeup parts, we have to use the plastic material as a support, and we have to manually remove the support afterward. And right now we are using the Ultimaker, which has the dissolvable material as a support. So we just create the support as usual, and then after it prints out, we put it in the water, wait for 24 hours. And the second part is about how to tell the user which orientation or which printing settings could be the best for the printing, right? I think we didn't have that part in the tool, but since we have the mechanical experiments and we have the results, so possibly in the future we can add that feature as well. Yeah, thank you. That's a good idea.
Hi, Chiun Kim from Texas A&M. So it seems like you have tested with different external geometries, such as like a star-like springs and the square-style spring, but all these examples are the cylindrical. So is there any like side effects that you found out from all the external geometries?
You mean the spring geometry or the body or the model geometry? Spring geometry. So when we started this project, we explored different types of springs, and like a candy level, we also explored it. But since the helical spring has a space, it has some space inside. So we're thinking maybe it also can approximate the geometry as mentioned. So that's why we use a decorated spring. And also, as I said in the slides, the spring has three main benefits. Helical spring. They can do a lot of deformations like bending, twisting, right? But each other type of springs don't have that rich deformation behaviors. Yeah, and also later on we add the joints. So because we're using the space inside the helical spring. Yeah.
Okay, so I think we will end this session now. If we could thank Liang again for his presentation.